I'm Harold Hunt with the Real Estate Center at Texas A&M University. We're here with George King, Distinguished Engineering Advisor with Apache Corporation. So George, what does the average Texan need to know about fracking?
Basically, the environmental risks are fairly small and they are controllable. The benefits to the industry, however, are tremendous. Fracturing is used almost universally in nearly every well drilled in the United States. Over 90% of the gas wells are fractured and virtually 100% of the onshore oil wells are fractured. This is a stimulation benefit that has allowed us to drill less wells and get more production.
So could you explain in layman's terms what fracking and horizontal drilling is?
Certainly. I'll start with horizontal drilling. The first horizontal wells were drilled in the 1950s, and by the time of the 1970s to the middle of the 1980s, horizontal wells had become a standard way of developing reservoirs. Basically, to drill a horizontal, you start drilling vertically at the surface, drilling down past the fresh water layers and then through the upper rock developments. And when you're down several thousand feet, then you're ready to turn horizontal. But first, while you're drilling, you start with a relatively large drilled hole, then you put casing in the bottom and cement it completely back up to the top. You'll drill out of that past water zones or past mineral zones like coal, run another piece of casing, and again cement the surface. What we're doing is creating a pressure vessel by way of multiple barriers. In case one fails, the other one will back it up. And this is the way nearly all wells are created, just to be able to do the type of containment and isolation that is really needed in these operations. As you go down deeper, you'll make adjustments to the bottom hole assembly, and you'll start turning these wells from pure vertical towards the horizontal a few degrees at a time, and you make a smooth transition from the vertical well to the horizontal, looking something like a capital letter L, but without the sharp breakover at the bottom. When we're finished drilling and turning the corner, we stop the adjustments to the tool, and then with a standard string and a motor and a bit on bottom, we drill anywhere from a few thousand feet to over 20,000 feet outwards away from the well site, following the rock layer, which is our target. Once that is finished, the final string of casing is run and cemented, and then the well is divided up into sections on the drawing board and perforated, and then small fracture treatments are done all along the wellbore to increase the contact area of the flowable fluids back to the wellbore. And as we link up all of these fractures together, we have contact areas with the formation and the fracture that will total several million square feet of contact in a single wellbore. The fluids can enter in the smallest of zones, flow into the fractures, and then into the wellbore itself to be lifted by pumps to the surface. The marriage of the horizontal wellbore and all of these multiple fracture sets have really enabled us to produce these unconventional reservoirs in a manner which makes it economic. This in turn has boosted our reserves and our supplies of natural gas and oil.
You know, a big question with the real estate community is how long all this is going to last. Do you have any feel for the timetable?
The timing of any development depends on the size of the oil or gas development and local price structures and the presence of the infrastructure necessary to do our business. Normally on a large development like the Eagle Ford Shale, for example, which may stretch 380 miles long and over 100 miles wide in some places, this development is likely going to be around for years. Right now we're in the early stages of it, where we're seeing methods used that are literally what we know from other areas. But Formation and project-specific technology will be developed to make the Eagle Ford much more productive over the next decade or so. I expect this to be around for a long time simply because it has a huge amount of gas, oil, and the liquids-rich part of the gas, which will make propane and butane. There's all kinds of products to be developed out of this field. In a smaller development, it's not going to be nearly so long in terms of duration. But when either project is finished, you're going to have a core of people there maintaining and operating those wells for decades to come.
So I hear the term unconventional drilling a lot. What's the difference between conventional and unconventional drilling?
The drilling isn't that much different. Basically, we knew about all of these unconventional reservoirs before we thought them to be reservoirs. These are the source sands for the oil and gas that have accumulated in conventional formations. But the actual drilling itself is much the same. The different part about it is how we connected the horizontal wells and the fracturing. The fracturing volumes compared to early vertical wells that were fractured are actually smaller per individual fracture, but the total volume is larger for a well. But you have to remember that one horizontal well may replace 10 or more of the vertical wells.
So as far as numbers of people that are involved with this, do you have any feel for how many people are in the drilling side, the completion side?
For the first month to 2 months, the drilling crew will be there drilling a well, and each well will take them anywhere from 3 weeks to maybe 2 months, depending on the depth and depending on the rock strata and how difficult it is to drill through it. The actual fracturing process will last anywhere from 3 days to about a week and a half. And that will involve 10 to 20 people who will really maintain the fracturing units all around, and they'll move the fracturing units all around the field. So in this particular application, they could be there in that area for 2, 3, 5 years working on a large development. Now, when the fracturing is finally over, you'll have the facilities people that come in and build the pipelines. That will be over in a matter of weeks. But the operational people, the numbers of people that it will take to maintain, operate, and work on some of these wells, you're going to see areas like gas where only 5 or 6 people per 100 wells are needed, to oil and water flood operations where you might be in the neighborhood of 15 to 30 people per 100 wells. And so these people will be making a career in this area, and I've seen these particular large developments like the Permian, for example. I've seen 3 generations of people raised and working in that environment. So they can be there for quite a while in a big project.
So we hear a lot about depletion rate of these wells. Tell me a little bit, is depletion rate really that serious a factor, or what do you think?
Actually, it's beneficial for the way many producers operate. Think of it this way. You've got a 10-lane highway out there, and it's the middle of a traffic jam. You've got gates across the highway for some reason, and you've got that traffic stopped back for 10 miles. That's like oil and gas waiting in open natural fractures within the rock. Now, beyond that 10 miles, you only have a few feeder roads coming in with 2 lanes, and only a car or 2 can get there through there at a time. When you open the gates, or when you put the well on production, the traffic, or the oil and gas, flows in very rapidly because it is sitting there in the fracture systems already ready to go, and it flows quite rapidly. Now, when that has drained out, you get then the fluids that are coming in more slowly from the matrix of the rock or from these 2-lane roads that are coming in. And so what you wind up with is a lot of cash flow at the very start that helps you pay for your well, and then slower but very steady production that goes on for a number of years afterwards. So this is a type of a well that we're very used to producing. And this is somewhat the difference between the unconventional reservoir and the conventional reservoir. and you have a fast decline rate in an unconventional, but you get a lot of your money back up front.
So will you see a lot more wells drilled in this type of drilling compared to the old conventional system?
The numbers of wells are slightly higher for the unconventional wells, but what you do see is you're doing more hydraulic fractures down the lengths of these wells, and this gives you a much better contact area with your rock itself, and that's what's made these unconventional reservoirs possible. We've known that the Barnett, the Eagle Ford, the Marcellus, all of these reservoirs, we knew they were there years ago, but they were nuisances as we drilled vertical wells through it to a target zone and maybe did one frac on it. Well, they've been fracturing the Barnett, the Eagle Ford, the Marcellus for years. They've just never been able to make it produce, simply because it needed a different sequence of things to make it possible. The horizontal well and the multiple fractures in that are one of the situations that has actually made that work.
So regarding price, I hear people talk about break-even price, and if the price of oil or gas gets below this or that, that's a problem. Is there some way you can monitor a break-even price, or is it too varied?
You have to know the area that you're in and how much it costs to actually drill a well. And the more you learn about that area, the more the cost of that well comes down, because you're learning how to drill it more efficiently. Now, in terms of the break-even cost per the type of reservoir or the development that you're working with, if you are on an old infield type well where you know exactly where the oil is, you know how to drill it, you know how to stimulate it, you know how to produce it, your break-even price may be anywhere from $20 to $30 a barrel, maybe even a little bit less. If you are into an unconventional development though, and you're still doing a lot of research, you're still having to do some trials in the field, you're still having to try to prove the technology behind all this, then what you'll find is the cost to produce that oil and break even is significantly higher, often in the range of $50 to $60 a barrel. There are a few projects which people are experimenting with right now that the recovery price is probably over $100 a barrel. But as technology improves and their learning improves, that price will come down, and these may be conventional types of reservoirs, or at least economic types of reservoirs down the road a few years.
So are they recovering a big percentage of the oil and gas out of this shale, or is it something where a lot of the product is still left in it?
In gas, in the Barnett Shale, for example, until the late 1990s, they weren't recovering more than 1% to 1.5% of the total gas in place. Now, we're recovering somewhere between 15%, somewhere in there, up to over 35%. That's come about due to technology developments that have showed us how to more economically really produce these reservoirs. That's on the gas side. On the oil side, the first Bakken oil well, for example, was drilled in 1951, and from there through about the mid-1980s, the recovery was 1 to maybe 2% of the oil in place. Technology started being applied there, and now it's in the 3 to 5% range and headed probably towards 5 to 10% in the next few years. But it's a learning curve that we really have to find out how fluids flow through these really tight, low flow capacity reservoirs.
And speaking of tight, is there a difference between shale and tight sand formation?
The difference, the mineralogy is nearly the same in many of these cases, except for the shales have an organic content in them, and this is what has generated the gas and oil. Often they have been the source rocks to feed into conventional rocks. So the difference there is lower permeability in the shales, and you're looking at permeability of a shale being 2 orders of magnitude less than the concrete in a slab. And we're getting oil and gas from that simply by horizontal drilling, a lot of hydraulic fracturing and increasing the contact area out to a point where even a small flow from an area of rock will turn into a much larger flow at the wellbore.
A lot of people are concerned about the usage of fresh water. Is it a dramatic amount of water that's being used in fracking?
Texas used about 1.3% of its water for oil field operations and mining. So a very small amount of that water actually goes to fracturing. The biggest users, of course, are irrigation for agriculture and municipalities for drinking water. So the volume is low. Now, to put it in perspective, if we drill 20,000 wells in the United States, enough water to completely total all of the water used in fracturing in those 20,000 wells, more than that evaporates out of Lake Mead or Lake Powell in a single year. So in terms of how much of it is, 8 hours worth of Mississippi River flow into the Gulf of Mexico would equal the volume that we'll need for fracturing. The problem that we have, of course, is in many areas it's arid to begin with, and it really can't stand much more water withdrawal. For that reason, we're switching over as fast as we can to using the high salt water that comes out of the wells under normal producing operations. So this produced fluid, when mixed with a smaller amount of fresh water, can actually form the basis of a fluid that we can use for fracturing, and we accomplish our fracturing and cut down our usage of fresh water.
We hear a lot about the federal government and the EPA, that they may stop fracking or somehow cut it back. Is that a concern, do you think?
The EPA and other scientific government bodies, when politics are not included, have found that hydraulic fracturing creates no concern, especially to groundwater. And those are the facts that we want to get out. And it's been studied by a number of organizations, both academic and governmental, and we really have come out very well in almost all of those studies. So what we need to understand here is that fracturing is essential to the production of fossil fuels and hydrocarbons throughout the United States and Canada. The reason that some environmental groups are, of course, opposed to it is that fracturing is the great enabler of shale gas production, and they will argue that it keeps us from going to a renewable energy source.
Do you have any thoughts about, do disposal wells cause earthquakes?
Disposal wells may cause some minor earthquakes, but remember that that is 10 to 20 wells that have actually been linked to that out of 148,000 wells. And those have been very low-level seismic activity. Hydraulic fracturing has really never been linked with any type of major seismic activity. There have been a number of earthquakes that have occurred during fracturing, but they're about 5 to 6 miles below the point where we are fracturing in many cases. So we look at this, and the studies that have been done by the United States Geological Survey and both academic and industry researchers, and what we're seeing here is that we're really not seeing any link between hydraulic fracturing and seismic.
Thank you, George. We'd like to thank George King with Apache Corporation for being with us today. I'm Harold Hunt with the Real Estate Center at Texas A&M University.